Good morning to all of you. Am I audible clearly?
Good morning, sir.
Yes, sir.
Good morning, sir.
Good morning,
Sir.
sir.
Good morning, sir. Sir.
Okay, I'll wait for 1 more minute, then we'll start. Meanwhile, if you have any question from the last class, you can ask me. Okay, in number synthesis, we have this is our second class on number synthesis. I hope this screen is visible to you, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Okay,
Yes.
right. This is our lecture number 3. And today is Okay. Happy National Youth Day to all of you.
Thank you, sir.
Um, so we are going to discuss today. In our last class, which we have discussed, is the this Kutzbach equation. So we were actually discussing here this. This is the. I mean, let me switch on the recording. Last class we were discussing degree of freedom of a kinematic chain, and we now shifted to degree of freedom of a mechanism. Degree of freedom of a mechanism. What would be the difference with kinematic degree of freedom of a kinematic chain and degree of freedom of a mechanism? What is the difference? What is the difference? You know, guys. It's very simple question.
The
A
kinematic
mechanism.
chain follows the equation this F equals 3n minus 1 minus 2g.
Hmm.
And sir, mechanism, for mechanism it is not necessary.
So only binary joints in mechanism.
No, what is the connection between a kinematic chain and a mechanism? A
Because
closed
a
kinematic
combination of kinetic energy.
a closed kinematic chain is called a mechanism. Okay, so then also this formula is valid. Okay, you can check for a suppose I'm writing this Kuchbek equation once again. Kuchbek equation say the degree of freedom of a mechanism is 3 into n minus 1 minus 2j, where this n is the number of links and j is the number of simple joint. Okay, so for a 4-bar mechanism, let us test this. For a 4-bar mechanism, just draw here a 4-bar mechanism. Link number 1, 2, 3, 4. Okay, how many joints are there? R1, R2, R3, R4. So here n equals to what? For this example, n equals to 4 and j equals to 4. So from here, what is f? 3 into 4 minus 1 minus 2 into 4. What is this value?
1.
1.
And from your physical inspection of this mechanism, what is the degree of freedom of this mechanism? Your this link 1 is fixed. What is the degree of freedom of this
One.
mechanism?
One.
1.
Degree of freedom is 1. All of you convinced that degree of freedom of this whole mechanism is 1. Are you convinced or not?
No, sir.
Yes, sir.
Okay.
No,
Okay.
sir.
Okay. Okay. Let us discuss. Suppose I give one, means if it is a open kinematic chain, then what you would have done, suppose this end is sorry, this end is open. Suppose this end is open, then what you would have done? So what you can do, you can assign one coordinate system with this theta 1, and then this is theta 2, and then you can say this is theta 3. Okay, so that gives you the number of coordinates required: 1, 2, 3. Three number of coordinates. But then, if suppose this is hinged at this point, this is not open, this is hinged at this point, then then you can always have relations, like if you uh, see this length of L2 is known to you, this length of L2 is known to you, all right, and then this length is also known to you. So at any instant of time, you can draw this kind of circles. If you, obviously the length of these links are known to you, you can draw this kind of circles,
Sir,
and
cursor is
then
free.
huh?
Freeze हो गया cursor.
Okay, I mean I'm drawing this red
अब दिख रहा है sir.
arcs. Okay, red arcs. This red arc, and there is another red arc like this. So these two arcs are known to you. Now, at any instant of time, if you just put your compass and try to try to see where is the third link. Suppose at any instant of time, we have chosen one point on this arc. Okay, on this arc you have chosen one point. That means you want to say at that instant this is link 2. Okay, this is link 2, and so for that instant you can use your compass and you can draw the, already you have drawn the other arc, this arc. On that arc, depending on the length of link 3, you can draw another arc making this point as center, and that point is your now R3 point. So you have this link 3 is here this way. That means what? From this, one thing you must have noticed, that only we have specified this angle theta 1, and other two positions, this other two position of this link 3 and link 4 are obvious from this theta 1. So that means what? That means this motion of link 3 and link 4 are related to link 1. This is physical inspection. Okay, from the physical inspection, you can see that this link 3 and link 4, their motion is not independent. Their motion is related. Okay, how they are related? They are related by this geometric relation. Okay, so this way, only independent coordinate required to specify the configuration of the system is this theta 1. All right, other two are not necessary. They will automatically come. They will automatically come from this geometry. Okay, is it clear?
Yes, sir.
Yes.
Yes,
Yes.
sir.
सर
Yes,
एक्सक्यूज मी
sir.
सर
हाँ बोलो.
सर अगर फोर्थ वाला क्रैंक हुआ तो वो एक पूरा सर्कल रोटेट करेगा, तो उस केस में सेकंड वाले से जो हम आर्क बना रहे हैं R3, एक
Yeah.
R3 ये ऊपर बना, एक और नीचे साइड भी बनेगा, तो सर तब तो उसकी दो पॉसिबिलिटीज हो जाएंगी.
Yeah, you can have two possibility of so that's a good question. One must understand the question. He is saying about two possibilities. Yes, you can have two possibilities mathematically, but once you have your mechanism is working, You cannot go suddenly from this position to another position. Okay, can you go to that? You cannot go.
Sir, you
There are
can't directly
always
jump, but to predict from one given
no,
angle.
that kind of jump is not possible. Okay, from one position to another position. Only there obviously there are few situations where it may happen that at that situation basically those are called dead centers, and that at the dead centers you really don't know whether mechanism will follow the forward path or backward path. Okay, we will discuss some of the situations like that, but that is another issue. What I am trying to say here is, you know that this theta 1, depending on the theta 1, theta 2 and theta 3 can be determined. Are you convinced with that or not?
Sir, I'm convinced with that, but if only theta 1 is given and they're asking about where R3 should be, then what to do is my question.
No, that is another question. What we are discussing here, that is separate question. What we are discussing here is the dependent of these coordinates on each other. Okay, that is separate topic, we will discuss separately. Now we are interested in the degree of freedom of a system. So you are convinced with that key theta
Yes,
2
sir.
and theta 3 depends on theta 1. Let's not divert with this topic. That is a separate issue we will discuss. Okay. So
Okay, sir.
So from here you can see that we need only one coordinate to completely specify this mechanism, and from this formula also we are getting the same thing. Okay, so the degree of freedom of this mechanism is given by this. Now we will discuss some of the spatial situations. Okay, uh, one of the situation is, suppose there is a higher pair in a mechanism. There is a higher pair. There is a higher pair in a mechanism. So let me draw a higher pair. It suppose it looks like this. What do you mean by a higher pair?
Having point or line
Point or
support.
line contact.
Point or
Point
line
or
Point or
contact.
line.
Point to
Point or line contact.
and
point or line contact. So I am trying to draw a higher pair here, which is a not very real but hypothetical higher pair. Suppose this is a hinge point on one link, and this is another hinge point on the link. Okay, so this is our link 1 and this is link 2. This joint is a higher pair, this joint, right? This joint is a higher pair because there is a, for this drawing there is a point contact. All right, or actually when you consider thickness of these two links, then there is a line contact, right? So let us put
Yes, sir.
some name. This is, let's say, O1 and this is, let's say, O2. Okay, now the question is, what is the possibility of motion with this between link 1 and 2? What is the possible motion between link 1 and 2? What is the possible motion?
Sliding rolling.
Yes,
The
they can,
rotation of both.
yes, they can rotate with respect to each other. Rotation and sliding. Okay, but now let us understand what happens at this instant. At this instant, what is happening? If you consider the contact point here, we are saying it can rotate and it can roll. Okay. Now, if you just draw the common normal to both the contacting surfaces here, so imaginarily that will be a line like this. Okay, that will be line like this. All right. Now, any any rotation is always about some point, right? And sliding about which point?
Point of contact.
Infinity.
The center of rotation, if we take infinity, then that is sliding. Okay. But in this case, you see that we can present this rotation, okay, this rotation and sliding at this instant. At this instant, suppose this is the common normal which is drawn here at the contact point. Okay. Now we can always find out the center of curvature of this surface. Suppose the center of curvature for this surface, center of curvature for this surface is, let's say, A, and center of curvature for this surface is, let's say, that is, uh, let us take it here. It is not exactly there, but it is here. So let's take this is point B, center of curvature of this surface. That means, so any motion here can be represented as rotation of this link 2 with respect to point B, and the motion here can be presented with respect to point A. Now here a point you must note that this line AB is changing at every instant. This is a particular instant. At the next instant, this line's position will change. Also, the point A and B, their position will also change, because you see this is not a circle. Okay, this is some other. Obviously, this surface is a smooth surface. That means there is no discontinuity in the in this curve, but this curve is not a circle. That means this point A is not a fixed point. At the next instant, suppose this link goes to, suppose the whole thing is rotating in this direction, so this link will come to some position here. And at the same time this will also have some other position. For those two positions, this line will no more be this AB line. This line will be something else. Okay, so we have to consider the equivalent, some equivalent we want to we are trying to find out here, and that equivalent is valid for a particular instant. Okay, so we can say from this argument we can say that this, at this instant, this whole higher pair can be represented by this lower pairs, because the motion can be represented at this instant. Remember always that at this instant the motion can be represented by this mechanism which I am drawing here below. This is one link, and that link is O1A, and we have, this is the other link, which is A, B, and we have another link here, which is O to B. So at this instant, the motion can be, the whole motion can be presented by this. So this is the instantaneous equivalent. We can say instantaneous equivalence of the original higher pair. Okay, now what actually we did here is we have now represented this higher pair in terms of lower pairs. So one higher pair was there, now that is equivalent to two lower pairs. Okay, now we will take one practical example to understand this. So actually we are claiming here that one higher pair is equivalent to two lower pairs. Right, now let us take one example. So you can consider a CAM follower mechanism where you have a link like this, which we generally refer as CAM, and which is connected to link like this. And that is guided by this fixed link. So how many links are here for this case? This mechanism, how many links are there? The fixed link
Three.
is 1, this is 2, this is 3. Okay, not 4, because this link is, this is a fixed link 1, right? So there are 3 links. Now you understand the motion. So if this rotates in this direction, what will happen to this link? The link 3, 2 rotates in this direction, link 2 will go, link 3 will go up and down, right? It will go up if this link will rotate in this direction, so this will push it up, all right? And if you arrange some spring here, then again when it will go down, right? So when this part of the surface will come in touch with this follower, then it will go down, right? So this is a CAM follower mechanism. And what is this pair here? What is this pair? This is a higher pair.
Higher pair.
Okay, but you can see that what now. Tell me what is the degree of freedom of this higher pair? So of this mechanism, what is the degree of freedom of this mechanism?
One.
It is
1.
1. It is 1 because you just give this rotation theta, and the other motion is definite, means you can get that from here. All right. So can we use our formula to have this degree of freedom for this case? Before we do that, let us see what is its lower pair equivalence, because this is a higher pair and we have practiced it right now how to represent a higher pair in terms of lower pairs. So let us try to do the same thing here. What we will do for that, first thing is we need to draw the common normal at the contact point. The common normal for this case is this one, right? This one is the common normal for this case. Now you can say that you can say that the center for this case, where is the center? We can have, I have drawn, I have not drawn it properly. All right, hold a minute. So maybe this is the, can you see this point I'm drawing here? This is the
Yes, sir.
Yes, sir.
point center of curvature of this surface of the cam. We are calling this is called cam and this is called follower. This is called cam, this is called follower. Right? And the center of curvature of cam A point is here. But where is point B, which is the center of curvature of this surface?
Infinity.
At infinity.
Infinity.
At infinity. So B point is at infinity, right? Somewhere at infinity. So now if we want to have the equivalent mechanism, then you know that this this can be presented as, so since this is at equivalent at infinity, we can say that at this point only this sliding, we can say that this motion is sliding. So we are drawing here, this is our, let's say O2, this is O2 point, and from O2 point to point A we have one link, right? And this link 3 now can be drawn like this, and you can say that there is a slider at point A which must be passing through a channel like this. Okay, because the other point is at infinity, we can say that this motion is a sliding motion. Okay, and your so A and B point is actually at infinity. So now for this case, how many links are there? This is 1, this is 2, this is 3, and this is 4, right? We have 4 links now. So can we now use that formula, the degree of freedom of this system? F equals to, have I used this? Okay. F equals to 3 into n minus 1 minus 2j. J is the number of simple joints. So in this case, for this equivalent system, but how many links are there for this equivalent system?
4.
4.
4.
4 minus 1. How many joints are there?
4.
1, 2, 3, 4. So we can also give name for your understanding. The joint names R1. Here you have R2. You have P. Let's say I'm calling P3 and P4. So there are 4 joints, right? Now, so what is this value now?
1.
1.
This is 1, which we have already we have discussed this, that the equivalent that the degree of freedom of this mechanism is 1. Now always we will not do this equivalent system, we will always not do this, but looking at this system we should develop something, that we should develop a formula. If there is a higher pair, then how can we calculate its degree of freedom? Okay, so if we write it like this, 3 into n minus 1. Another thing, if you compare this one and this one, okay, this one and this one, these two mechanism, the difference is what? Due to one higher pair, one extra link came here, right? There is one higher pair, one extra link. So number of higher pair, if I say that that is equals to h, then in this case we have this many links we need to consider, right? And then minus 2 into j. How many lower pairs are there in this case? Initially we have, this is one lower pair, another lower pair is here. So if I say that is the number of j in our mechanism, but actually when you do this equivalent, how many lower pairs are added? Two lower pairs, because one
2.
higher pair is equivalent to two lower pair, where we are saying h is the number of higher pair in a mechanism. Okay, now if you simplify this, what you get? You will have 3 into n minus 1 plus, here it is 3h minus 2j minus 2h. So we have f equals to 3 into n minus 1.
Sir, 4
सर माइनस 4h हो जाएगा ना
minus 4h.
Yeah, this is minus 4h. So 3n minus 2j minus h, right? Let us apply this formula for this cam follower mechanism. For the cam follower mechanism, what is this h? H का value कितना है? For the cam follower mechanism,
1.
1.
higher pair number is 1. What is this value?
2.
2. And how many links are there?
3.
3.
3.
3, right? And now if you apply this formula there, so 3 into 3 minus 1 minus 2 into 2 minus 1. What is this value?
1.
Okay. So now onward, if you have a higher pair in a mechanism, to find out the degree of freedom of that mechanism, you'll be using this. Okay. This formula. Let us go forward. We have some more special cases which need to be discussed here. We now will discuss here a case which is called redundant degree of freedom. Now, what is a redundant degree of freedom? We will write down the definition. First, let us understand what it is. First, let me write down the definition. If a link can be moved without causing any movement, without causing any movement in rest of the mechanism, then that then the mechanism is said to have a redundant degree of freedom. Now we take one example, and the example is like this. Suppose we have a link like this, and that link is connected with the other links like this. So this is a kinematic diagram of a mechanism where link 1 is fixed. Link 2 has a slot at the other end here, and on that slot, this link 3 is fitted there, and link 4 is similar to link 2. Now in this case, if you apply the formula which we have already derived, 3 into n minus 1 minus 2j minus h. If you apply, how many links are here?
4.
4.
How many simple joints are there?
4.
How
4.
many higher pairs are there?
0.
0.
What is this value?
1.
1. 1.
Now, tell me one thing, that suppose I want to give a motion to this link 2 in this direction. Okay, will this, from the physical inspection, you can tell me, will this have any movement, this whole mechanism?
No, sir.
No, sir.
It cannot. It cannot. But then what? Why this 1 degree of freedom is there? What it signifies? 1 degree of freedom. You can see one thing, that if you move this link in this direction, link 3, move link 3 in this direction, what will happen? Link 3 will move, right? Nobody is stopping link 3, because link, these two slots at this instant, at least the slots at the end of link 2 and end of link 4, these two slots are parallel to each other. Then if you try to move this link 3 along this length, along this straight line, it can move freely. Agreed?
Yes, sir.
If it can move freely, that means that is a degree of freedom. In this mechanism, that is a degree of freedom. But that degree of freedom means if you are moving this link, but that is not affecting rest of the mechanism, because the rest of the mechanism is fixed here only. So then this degree of freedom is called a redundant degree of freedom. So we need to identify in a mechanism. Sometimes it happens, you pose is your so the common question would be, why we should have a redundant link or redundant degree of freedom. Sorry, this is redundant degree of freedom in a mechanism. Sometimes from the structural point of view, or to have some other advantage, you provide this kind of link in a mechanism. But we need to understand whether that degree of freedom of the link is a effective degree of freedom or not. So in this case, you can see that that is not effective degree of freedom of the mechanism, because the whole mechanism is not having any motion due to the motion of this link 3. Then for this mechanism, what is the degree of freedom? Because this is a rigid thing. You cannot rotate link 2 or link 4. So the actual degree of freedom in this case is 0, right?
Yes.
No.
Yes.
Okay,
Yes, sir.
then we want to make this is equals to 0. So that can be done by adding or subtracting a number with this formula. And suppose if I use this fr here and say this, for this case fr is equals to 1, and which is the fr is the uh, we can say this is the number of redundant degree of freedom. Then this is sorry, this is equals to 1, and when you subtract this is equals to 1, you have 0. So in a mechanism, when you try to find out the degree of freedom of this mechanism, then you need to look at the mechanism whether there is any redundant link or not. Sorry, any redundant degree of freedom is there. Okay, so let us take another example for this case. Right now we have discussed a mechanism which is called cam follower mechanism. That is a translating cam follower mechanism. Now let us try another cam follower mechanism where we have the cam is already I have drawn. Now this is, say, this is the follower. This is the follower, and follower is hinged here. So when the cam is rotated in this direction, the follower will also have a motion, and that motion is oscillatory motion. Do you understand this motion?
Yes,
Hello?
sir.
Yes, sir.
Okay, now tell me what is the degree of freedom for this mechanism?
One.
How many
1,
links are there?
3,
3 minus
3,
1 minus 2. How many simple joints are there?
2,
2,
Two.
2,
How many higher pairs?
1.
1,
So this is 1. And right now there is no redundant degree of freedom. Okay, I'm writing here. This is H, this is FR, this is J, this is N. Right. So now what you are getting from this formula?
1,
One.
1. Okay. The same mechanism, let us now modify a little bit. So same mechanism we are drawing here. Other than directly a sliding motion, we are using a roller at the end of the follower. Okay, let us give the names 1, 2. This fixed link is 1. This is link 2. This is link 3. Fixed link is 1. Now, in this case, this new case, how many links are there? Fixed link is 1. And let us call it link 2. This is link 3. This is link 4. Okay. Now, what is the functional difference between these two examples, this one and this one? In this case, the follower rotates in this direction. Sorry, the cam rotates in this direction, and follower will have, what is the motion of the follower? Again, the follower will have a oscillatory motion like this. Convinced? Hello?
Yes, sir.
yes, sir.
Yes.
Yes, sir.
Yes, sir.
So functionally, their purpose is same, right? This mechanism and this mechanism. The only advantage is here you have a frictional contact between this link 2 and 3, but here you have a rolling contact between link 2 and 3, right? The advantage is when you remove frictional contact, you remove the chances of overheating, right? Because rolling, you have less friction. But the operation, means function you are getting from this mechanism, is same. But in this case, now if we want to find out what is the degree of freedom of this, then how many links are there?
4, 4,
4.
4 minus 1 minus 2 into
3,
how many
3,
simple joints? 3.
3,
3,
And then you have how many higher pair?
1,
1.
1,
1.
1 higher pair. Okay. Let us, for the time being, let us not talk about, tell me what is the, if there is any redundant degree of freedom. Let us talk about it
One.
later. Let us talk about it later. Let us find out what is happening here. What is this value?
2.
This
2.
is 2, right? But from the physical inspection, already we have done that. The motion which is given by theta, and that is related to this oscillation phi. Okay, that means the degree of freedom for this case is 1. That obviously we know the degree of freedom is 1, but you are getting 2. Why? Because there is a redundant degree of freedom. Can you tell me where is that redundant degree of freedom?
3.
Rotation of
Roller.
10.
Roller.
Rotation of
3.
3.
3.
Rotation of
3.
3. Okay. So here because if you rotate 3, then also it cannot change the motion. Okay, it cannot insert any special condition on the whole motion of the mechanism. So rotation of link 3 is redundant degree of freedom. Then we must deduct that number from here. So this is 1 degree of freedom. So these formulas we will not apply blindly. Okay, we need to check whether there is any redundant degree of freedom, whether is how many higher pairs are there, and now
Excuse me,
if
sir.
I, bolo.
Uh, Sir, if there is friction present between roller 2 and roller 3
Hmm.
in the last example,
Hmm.
then if you attach any motor to number 3, then it will cause number 2 to rotate as well. And so number 4 will also oscillate.
Yes.
So, sir, then it will not be redundant anymore.
Okay. Uh, I see your point, but yeah, then I believe that then this, if you consider friction due to friction without slipping, then this contact, the this joint between 3 and 2, what kind of contact is? So you give a particular motion, definite motion, and that definite motion is converted to 2. Okay. So how many, I mean, what I am trying to say is this higher pair will no more be there. If you do like that, this higher pair will no more be there. Will it be?
It will still be a point contact.
We are missing something. Let me see it. No, actually, what is happening here when when there is a definite relation between this motion of 2 and 3, this higher pair concept is, I think it will not be there. Okay, I will see this, and in the next class I'll tell you about this. Okay, I need to check.
सर यहाँ पर अगर फ्रिक्शन कंसीडर होगा तो फिर लोअर पेयर में कंसीडर हो जाएगा क्योंकि फ्रिक्शन तो एरियल
Exactly.
कॉन्टेक्स्ट से होता है.
Exactly. That's what I am trying to say, but let me take it this way. I will think about it and I will think how to explain it properly. Yes, that is the case, because this will no more be a higher pair, but how can I describe it properly tomorrow in the next class? I'll tell you. Okay, that's a good question. Already time is up, but I'll take one more example related to this. The example is, suppose the same mechanism like this, if I have a situation like this. This is one link hinged at this point, and you have, suppose, another link is like this, hinged at this point. I have this link passing through this, and it is a rigid link which is bent like this and passing through this, right? Generally, any bending, it present the kinematic diagram is presented like this. These lines are parallel. Now tell me, what is the degree of freedom of this system?
0.
0 sir.
0.
ठीक से बोलो.
0.
1.
ठीक से बोलो.
So 1 sir.
1 होगा.
Those who are saying 0, explain करो. And those who are saying 1, somebody can explain. This is no more. This is no more a redundant degree of freedom. Right? You're redundant nahi na. If you move it in this direction, that will cause rotation here and rotation here. Both the rotation, this rotation and this rotation, if you move it, then this is no more redundant, and the degree of freedom for this case is, let me put it this question mark, this is actually equals to 1, right? We stop here today. The lab class is there from 1 p.m. but we don't have lab assistant there. I don't know how to perform. I will take the मोबाइल फोन मैं ही पकड़ूंगा और लैब भी मैं करा दूंगा, बट आई डोंट नो हाउ. So when you guys are coming to the institute?
सर कब बुला लीजिएगा?
सर जब बुला लीजिएगा.
सर जब एडमिनिस्ट्रेशन बुला.
That is, I want you guys right now here, but nothing depends on me.
सर यहाँ पर जो क्वेश्चन लास्ट में डिस्कस किए हैं इसमें जब हम
Yes.
लोग ये जो बीच में फिक्स्ड लिंक है इसको जब मूव कर रहे हैं तो इससे दोनों का मूवमेंट कैसे हो जा रहा है? वहां तो फ्रिक्शन नहीं है तो वो दूसरे को कैसे ले रहा है? वो तो फिर अलग ही रह जाएगा।
थोड़ा सा सोचो, ये उतना डिफिकल्ट नहीं है, because when you move this link, in this direction, ठीक है, in this direction, let us draw that moved position. Suppose you moved to this position, okay, this point come to this here, that means this point will also come to the here. So actually your link should be at the next instant of time, it should be here, right? This link at the next instant of time, it should be like this. How it can be like this? When this link 4 is rotated, okay, to some position where it can accommodate, maintain this joint. ठीक है?
यस सर।
Any other question?
Sir, in that above roller question, if you consider friction, then you can relate the rotation of both things, no? Like V is equal to omega r. So there will only be one degree of freedom. It won't be independent anymore.
These are the different ways to justify the same thing. Okay, whatever you are saying, I have said that. Now, you know, sometimes we have to present your idea in such a way that it should be convincible to all of you, right? I'm trying to find out that. Once I get that, I'll tell you.
Okay, sir.
Okay. One thing is very clear, that the degree of freedom is 1, right? Because 1 means how we actually say the degree of freedom is 1, because that's what we are coming to that definition. In the next class I will discuss that. So one definite motion, one motion to one link, and you get definite motion to other link. From the other links you get a particular motion. Always if you give 2, you will get some 4 5 like that. Means you rotate it for, let's say, 30 degree, that will give you a rotation of 10 degree, or some link will give you a translation of 10 millimeter, like that. And that is fixed. When that is fixed, that means they are in a definite relation. Okay, that means you have only 1 degree of freedom in the mechanism, that is fixed. Now we need to understand, suppose this is a simple case, but suppose you are uh, analyzing a very complicated mechanism. Okay, so many links are there, they are connected, and then you need to find out whether your mechanism is having 1 degree of freedom or not. Then you need to think about what is happening. For those cases, we must understand these simple things. Okay, we'll discuss it in our next class. Right.
सर लैब क्लास सर होगा या नहीं?
लैब क्लास तो होगा. No class, कोई क्लास मिसिंग नहीं जाएगा. All the classes will be there in time. I need to devise how I can take it.
So
And
lab
that
assistant is not able to join, sir.
is,
Lab assistant sir join नहीं कर पा रहे MS Teams sir.
you are not helping him.
Yeah,
You
I was
guys.
helping him, sir. He
No,
don't
you
have
guys
the.
are not helping him.
I was helping him, sir. He don't have password for that, sir. I told him to ask from webmaster, but he didn't did that.
So that's a situation here, but I will take your lab in time. Okay. Any other question? Class is over. People can log out, and I'm just waiting
Sir.
for some questions. Bolo, bolo.
Sir, I do have a request. Sir, actually, when sometimes due to poor internet connection, we do get disconnected, then we are not able to join.
Mhm.
So, sir, please solve
From
this
the
any.
next day, and from the next day, it will be solved. Okay.
Okay, sir.
Okay. Any
Thank you,
other
sir.
issue? All right. Thank you for your attention. Let's see you
Thank you,
in
sir.
the in 1 p.m. maybe.
Thank you, sir.
So for the
Thank
lab
you, sir.
class, we have a separate link, right? You use
Yes,
that
sir.
link, and somebody was helping the TA for this lab class. Please help him so that he can log in MS Team. Okay. All right. Till then, bye.
Thank you, sir.